a problem or anything. Do you have a specific?
I just have to go through the last couple of lectures,
Oh, okay.
and the review had to do the centroid and moment inertia.
Oh, okay.
That's what the last two problems on the online final was about.
Yeah.
Uh, and just haven't been very well getting that concept yet.
Well, now I will say that if you go to, and let me turn this on, because one of the things about that let's see, I got to get that thing going. Yeah, I'll get it. There are some videos. Of course, I did a couple problems, and I did one the other day. And one of the things about it is I did do it. There is an integration on there, isn't there? Isn't there one integration? I think there's one integration on the online final. On the integrations, in the book, he does them one strange way, which is okay, but it's not what you were taught in Cal 3, I guess, or maybe it's Cal 2, where you did. Oh, okay. So in that, you were kind of taught something different. So it turns out they're the same thing, and that, like, was it last lecture or the lecture before? I did one in which I did it one way, then I did it the other way, and it essentially was the way he would have done it. But you can flip them. So it's, you could do dx dy or dy dx. You just have to be careful, which one you put first.
Yeah, that was Cal 2.
Okay, okay. So it's a little weird, but once you get in the mode of doing that, now on the in-class final, I'm not going to put one of those in there. So I'm just doing that on the. Okay, so this is different. Okay. Okay, let's see.
Is that going to be Thursday?
That's a good question. Let me see if I can. Let me first get here. Okay, that's here. Oh, I don't have the projector going. Hang on. That'll turn on in a minute. Let me get this. Okay, let me do that on this one, because then it'll be on the stream. Okay. So let's see. That would be ATU finals. Let me see if they've got the exam schedule. Okay, for spring. Boy, I hope they did the same thing that they sent to me. God, I hope they did. That would be a nightmare if they didn't. Okay, so it's currently 11 o'clock. It's on Monday, Wednesday, Friday. I think, wait a minute. So it's Monday, May the 2nd at 10:30. So I've got this test, and I've got that one. So it's Monday. That makes sense. And so what I'm gonna do with that is, I've got part of it made, and so what I'm trying to do is not deep problems, but little shallow ones that are like, okay, here's this, and I'll ask a question that's like, the problem itself could be like 5 steps, but I may ask just the first step. There's one that I ask the first and second, and then that's it. I don't ask anything else. So I don't want to do that and have people spend a lot of time. Okay, so this is, I guess it's that time period. And so my goal is to do little short sections, like I'm going to go back to the rope because there's nothing here that is completely separate from anything else. For example, if you get the rope, you're pulling on a rope, you got to find the direction in order to get the force and stuff. So I could ask questions about the rope, about the length of the rope, about the angle, things like that. Or I could go to one big, huge problem and ask you something real complicated, in which you got to find the rope and got to do that. So what my goal is to jump through the things along the way, little bitty parts in each part. And I think that's probably a good way to do it. So I'm going to do, like, for example, I'm going to do a truss, but I'm not going to ask all these members. I'm probably just going to ask one member. So what's the stress in that one member? And you can decide how you want to get there. If you sit back and think about it for a minute, you could say, oh, wait a minute, I don't have to take 10 steps. I could take 1 or 2 and get that and be done. But if someone's very confused, they don't know what to do, and it's an open book and open notes. So if you start running around, oh my gosh, I know what to do, pretty soon you wasted, 30 minutes, where somebody else wasted 5 minutes. Yeah. And so when you see these problems, you look at them, you think about them. Okay, what is he asking? Okay, what's the easiest way to get the answer? Because a lot of times there's multiple ways to get it. And then if you do that, if you take that, I would say take a minute, at least a minute, put your pen down, look at it, think about what's being asked, then say, okay, here's some techniques I can do to get it, pick your pen up, work it. You'll find you'll probably get out of the final. It's a 2-hour time limit, I think. Yeah, it's 2 hours. You probably get out of there 30 to 45 minutes. But if you come in and you're the type person that just wants to immediately grind, you'll probably be there the whole 2 hours. Because you can take 2 hours to work a problem. You can take 4 hours to work the problems and still get nowhere. But if you sort of look at it, think about what's going on, you can get through it pretty quick. So that's the way I'm going to structure it. Structure it so that, for some people it might not be fun if you're willing to take a break and think about it. So what I'm going to do is I'm going to kind of go through the whole thing. Let me see if I can find, that's not the right. So I'm going to start in chapter 2. I'm not going to do chapter 1. That's just units. So I'm going to start even back here, stuff like that. And just, if you look back, that's the thing where you find a vector, you find its length, you do all that. Now, you use that several times later. And in addition of vectors, that's embedded in sum of the forces equals 0. So there's no reason to ask a question about that. So if you look at it, just a couple of these problems, most of them, I'll probably be stuck on a length because like that, there's your position vectors. There's the length of a rope, that's more natural. Here's a rope. Well, let's see. How do I get that? Oh, you have to do the pin. You get all that. So he's got this thing set up. So essentially he's got a rope stuck between a couple spots. Something like that. You're just like, I may ask the question, what's the length of that rope or something? Or if that is a rope, it looks like a rope to me. That might be. But then he's got all these other things. I might ask some angles, the alpha, beta, gamma. Then of course you can open your book. Forces along a vector. That, I don't know. That's subject. I may do that, but I'm not sure exactly. But then you get there and that's pretty much it. There's a dot product, which I don't know, I might ask something, but those are, instead of doing dot products the way he does it, I might do it a little bit different. And then you go, let's see, chapter 4, what's 5? I'm sorry, that was chapter 2, then chapter 3. Chapter 3, I think, is the first time he does some of the forces. So, you know, those are pretty good problems in a sense. You could go down here and do you know, like something like that without springs, maybe. There's probably one down there without it. I don't want to do springs. There you go, something like that. Something similar to something like that. But, again, instead of ask the thing and everything, just pick one. I might just pick one. Have you go through it and go on with that. Not sure I'm going to do three-dimensional systems. I don't know. I'll think about that. I'm going to make the test between now and next time, so that at least I'll know what I'm going to put there. Maybe I'll kind of come back and mention a little bit better. But some of those aren't that bad, especially if you got something like this. Especially since that's 2 and that's 2, and that's 3 and that's 3, and that's 6. It's just a shifting of numbers. So it's not that bad. Now, if I went in and did really oddball numbers, that could be not so fun. I don't know. I like these bucket ones, but of course this one's on the other final already. With okay, except this is a rod because I had to make it a rod because sometimes it's in compression. And you can't do that with rope. Did you get it though finally?
Yeah, I eventually got it. Realized that we had to find the unit vector
Yeah.
for each one of those.
Mm.
Make it by whatever the forces you want to weight, and then you get what each one of the forces are.
Yeah.
Yeah, that made sense eventually.
Yeah, and that's the reason I do the test that way is that you get 5 tries because during that you kind of get it eventually.
Yeah.
And so and that's the goal here. The only reason I'm doing this final is that I basically said that I don't know. So, and I don't want it to hurt anybody. So there are people who will not need to come take it. And so if they don't, that's okay. There's some people that will not need to come take it, but will come take it anyway. And, if they score a bad grade, it's not going to hurt them anyway. Actually, it can only help you. Yeah, I was going to do it over the weekend because I was going to put that thing in there and rechange the email, but I'll send out a grade report later. And I'll send one out. I'll start sending one out each time so that people who are working those problems, can get a feedback as to where they are. So, especially when it comes time to deciding, I mean, you can decide whether you want to come in or not. That's kind of up to you. So this is all of that. And then the next one's moments. And the moments could be thought of as being hard, but I'm going to approach them like just a simple. Okay, so apparently I'm at the very end of that chapter. Oh, yeah.
I finally got it on the midterm and the final. But there are like ratios or distribution on the right and on the left side.
Right.
I just had to figure out what they were. But getting the resultant for the distance was it was simple enough.
Oh, okay.
But where in the book does it say you would find the left and the right happen if it was up?
Well, that's a good question. Here, let me drop this keyboard off. And the thing is he probably should put them in a single location. But if you look, okay, here he's not doing any of that. He's just telling you where the loads are. And then I think since we're in 4, I'm going to try to see if I can find 5. I need to, I'll tell you what, there it is. I'm going to put the 5 and drag it right under the 4. If you go to 5, and of course I'm going to have to go back to the top. So he starts with this free body diagram thing. And so these are the type forces you can have. So if a roller's sitting there, you can only, the roller will roll left and right. That's a terrible picture. So that it won't produce a force back that way, but the pin will. So he's kind of leading to this here, the support reaction. Then he goes through how each of these get supported. And that's probably a good thing to look at and review. Like there's a little rocker. So if the beam moves to the left, and it obviously has a little bit, then the rocker just rocks. It's basically just going to make it so the force goes straight up through there. So then you get down here, he talks about this, talks. And there's where he starts. Now this is the first one where he's like, okay, I do a free body diagram, meaning I cut the wall out and replace it with the reactions that occur at the wall. Now I need to find what those are. And to find what those are, you do the sum of the moments about some place equals 0. Sum of the forces in the x equals 0. And the sum of the forces in the y equals 0. And you'll notice, well, it's kind of weird that he does this way. You'll notice, here, let me go to the next one, because he probably starts doing it here. Okay, so here's an example. And again, my picture isn't that great. Looks to me like these are just, gosh, I can't really tell. Looks to me like that might be a rocker arm. And this one's a pin. So what he does is he takes the reaction, he replaces the physical picture with the forces that could be there. And then he looks at this diagram. And of course, what he's doing here is he goes ahead and breaks this down to its x and y components. And then he says, okay, I need to know this, know that, I need to know that. And so then when he comes up here, first thing he looks at, it looks like he's going to go for the x one. And so when he goes for the x, you only have that force, and you only have that force. So he has this one, and then he has this one going in the opposite direction, and that gives you the B act. Then what happens to him is he says, it looks like I got it. Well, it looks like his next thing he decides to do is he wants to sum the moments about B. And one of the advantages there is if you're summing the moments about B, then these two forces don't produce a moment. For that matter, that one doesn't either. And neither does this one, even though it's on the top. Well, no, wait a minute. He is giving the distance. Okay. He is giving the distance here times that. So it is on the little top. So what he says is 100 times 2. It's 100 times that 2. The 6 times 5. That would be, let's get too clustery now. Getting that, this times 6, or should be 5. Oh, I'm sorry. That is 5. That's 5. So he's got that for the moment. Then here's his little bitty moment arm. He takes this one times the 0.2. The 0.2 is that little distance right there. And then this is this little part right on the top of the beam. And then what he does is he takes that last one, which is the AY, and then there's your 5, and then 2 more, that gives you 7. So then he just solves that through, and he gets that AY is equal to 319.
So you just use some of the moments find the reaction forces on it.
Right.
Okay.
Yeah. You can actually, so what's clever is you can do some of the moments about one spot, and some of the forces in the X and some of the forces in the Y. That gives you 3. And you'll notice he has 3. Now, you actually can kind of trick it and replace one of them with the sum of the moments. In other words, I could, if you think about it, if I sum the moments about A, then one of the unknowns is the B. This one doesn't show up because it's right in the center. So you can actually sum the moments about A and get the solution to BY. Then you can do like he did. You sum the moments about B, and as a solution, you get AY. So you can use sum of moments a lot of times. You don't have to always use some of the forces. Sometimes if you're clever, and that's why I was talking about, you sort of pause for a minute, take a look at the problem, say, hey, wait, what am I doing here? You can figure out how to, you can solve it another way, plus you can have that other way to check it. In other words, you can go back and check it by having 2 different ways to find that force. And so that
where it asks for a certain point, it's like to the left, you go to the right.
Yeah.
I need to determine those because I've gotten them wrong every time.
Oh, okay. Now that's in chapter. Let's go to that one. Let me think about what chapter that is. Okay, wait a minute. I'm going to try to line them up again. There's chapter 6. Okay, so chapter 7. Oops. Wait a minute. You can't use your finger and that, apparently. There's chapter 7. So let's see. I'll put that right here. Then chapter 8. I don't think it's chapter 8, but I'm going to line them up anyway, if I can find them. There's chapter 9 and 10. Anyway, I think I'm going to skip 8. It's in there somewhere, but let's see if I can find which chapter that is. That's the trusses. This, I believe, is it. So the way this works, okay, so first there's this weird sign convention, and that sign convention gets stuck with you because of mechanics and materials, and you'll find that out later. So you just want to keep that. So what it, like, for example, in this one, if you're looking at B, B is just to the left. So what he's going to do probably is come in and find that load, AY, and then what he's going to do is he's going to take the problem and slice it. Just since it's just to the left, you don't have anything there. There's no load. So in other words, let's say I'm going to cheat and find out what his AY is. So his AY is 5 kilonewtons. So here's your AY, and I'm just going to say 5 kilonewtons. And then I'm going to say, here, let me get that keyboard out, because then I can snip it. I could snip it without the keyboard, but maybe I'll try that. Here, let me just snip it without. I think we'll do this one. Okay, new. Here's what I'll do. Come in here. And so if you snip it just to the left, you don't see anything there. And then you can go in here and just go right there. Well, now I do need the keyboard. Okay. And so now you're going to have to find the shear. Now, if I go back to the book, and I'm going to try to be very official and go to right here and say I'm looking at the left end. The left end positive is pointing down. I'm going to point that down. Here, change the, point that down. I know the moment is positive here. And then I know, wait a minute. I just want to double check. Positive here goes to the right. So first of all, if I look at this picture, sum of the forces in the X tells me the normal is equal to 0. Sum of the forces in the Y tells me that this V, there's no other force but that 5 kilonewtons. So that's just V is equal to 5. And then sum of the moments equaling 0, but what I like to do is sum the moments about the point that you sliced. Okay, and if I just do arbitrarily that, then I basically have M, because that's that. And then only if this doesn't produce a moment because it's right there, and neither would this, even if it isn't. So the only thing I get now is 5 kilonewtons going this way around B, which is the opposite of positive, which is 5 times 3. So move that around, I get the moments equal to 15. So I get this equal 15, this equal to 5, oops, here, equal to 5. Now, let's say I came back to the book, and this time I want to know the one to the right. So if I want to know the one to the right, I take my snippet tool. This time I have to include that force because it's to the left. Then I go back over here. I can slide down a little bit, take my new picture, and say, okay, now what do I got? Well, before, let's see, there's nothing new here. There's the normal is still going to be equal to 0. But now, okay, so here's my shear, and there's my moment. Those are both positively defined. So sum of the forces in the Y equals 0 tells me I've got 5 minus a 6. I got 5 up, 6 down, and then V down. And suddenly I realize I got V is equal to minus 1. Is that right? It's 5 minus 1. I get minus 1 minus V is equal to 0. So I can move it. Yeah. So I get that. Now here's the trick. When they're saying these in the book, they're kind of saying the distance from here to here is kind of like 0.00001, you know, something so small that it's just slightly there. So what that means is when you go to some moments about that point, which now is C, I think that's point C now. So when you go to some of the moments about C, this 6 kilonewton doesn't produce a moment because it's so ever so close to C that it's not there. Does that make sense? And so then what you get is you still get, believe it or not, you get the same answer you did in the one before. You got the, first of all, you get M if you define this as positive. Then you get the 3 times the 5, and that's just 15. And this doesn't produce anything, so you still get the moments equal to 15. So if you look back, let's look back and see if, oh no. Oh, okay. Okay. All right, so that, okay, so that moment on that end did affect this, but I cheated and I went down and I picked that up. Here's what I mean. I said, oh no, because of this. If you look at the support reaction, what he does is he goes in and says, what's the moment about D? He takes the moment about D. It is true there might be a force here, but he says 9 this, 6 times 6, 6 times 6, minus A times 9. There's your 9 and there's your A. So since I copied that, but the reason, you know, in other words, if you turn this 9 into 90, say you turn that 9 into 90 and you start increasing it, the more and more and more you twist, the higher this load's going to become, if you think about it. So I said, oh no, thinking, oh no, I didn't see this, but I simply copied the AY off of here. So the free body diagrams, okay, segment AB. So here you get the VB, and then this. And notice what happens. Segment this, it's -1, but the moment's still the same. And of course, this is never anything because nobody's pushing it. So, does that kind of make sense? So if you go into chapter whatever this one is, 7, he's spending a lot of time. Well, no, wait a minute. Okay, so here he's doing internal reactions. The previous one we looked at, which was, what was it? 5? No, it was 6. Was it 6? No, it was 5. The 5 is telling you how to do support reactions. Once you do the support reactions, figure that out at 5, then you can go to 7, and then you can do the internal stuff. And so what you notice is all of them. So for example, here he removes the wall and replaces it with, you notice his rendition of what's positive, and what's positive. And that's the thing. This is the one area in statics that you got to follow the sign notation. The rest of them you can, in other words, I can sum the moments equaling 0 about some point, and I can make that positive or that positive. And that's true. The difference is you got to draw them in these particular ways because you'll find out later in mechanics and materials that that's really pretty important. So then what you do is get rid of the supports, replace them with the load, and then you just, like he's doing here, sum the forces X, Y, and then the moment about some place, usually the best place is the place where you're interested in finding the internal load. It could be labeled, this time it's labeled as C. Other times it could be labeled as something else. So here he's probably interested in finding out the load at B. So first thing he does, he finds the support reactions. And so he's going to be looking for the load here and the load here. This is kind of unique because this little bar, support bar, can only push this way if it's pinned in there. Okay, once he has this, you can do, and this is a good rendition here. So he's wanting to know the internal loads at B. You could do either this, THER, or that thing. You don't have to do either one. Whatever you find out for MB here has to be the same here, and this has to be the same as here, and this has to be the same as there. And you notice in either case, they're all equal and opposite reactions. In other words, this point to the right, that's point to the left. This is twisting this way, twisting that way, going down and going up. Right. It's the same because if you slice the bar and move the left-hand side and move the right-hand side, and you're doing it in your brain, you're not physically doing it, then whatever happens on this end has to happen exactly equal and opposite on that end. So, oh no, so it doesn't have to be anywhere you take it. So in other words, if we sliced it right here, it'd still be equal and opposite. So what you're doing is splitting them apart. So then the question is, do you want to work the problem on this end, or do you want to work the problem on that end? Sometimes it makes a big difference as being easier. Some of them can be easier than others. Some of them not so much. It just kind of depends. In this case, I don't think it matters. Not in this case, but in some cases it does. So which one does he? He wants to do segment AB, which that looks like that one. So what he does is sum the force in the X. He takes his 267 and makes that equal to it. Then, believe it or not, he does sum forces to Y. And just out of interesting this is an anomaly. This doesn't always happen. But it turns out that's the case. And then, you sum the force, you get 500. And he says this: as an exercise, try to obtain the same results using segment BC. And it turns out you always get the same result. It's just sometimes like, let me think about a case. I mean, here's a case where, let me just come up with a random case. Let's say you had somebody that had this, and then you had this, and then you had a force here, and then some kind of support here, and then you had the reaction here, and somebody said, I want to know the internal load here. Well, if you find this reaction load, and you slice it, and you do the left end looks like this. And you're like, hey, this is really good. I like this. The right end looks awful, has a whole bunch of stuff on it. So the right end is this. You'll have a load here, some sort of funny load here, some sort of distributed load here. And then you got to do everything. You got to include all these. There's more calculations on this one. The left end here doesn't have much. So you can make it easy or hard depending on which end do you pick. But either end you pick, you should get exactly the same answer. So it's really, it's kind of cool because almost all of these, I would say, really in statics, there are most, I'd say at least 50% roughly of the problems. There's a couple ways to work it, so you could always check yourself. Now, saying that and doing that is two different things, because sometimes you want to work it quickly. You may find that it may take you, 30 minutes to calculate it the long way, and so you may not have time. But if you have time, like that'll take you a lot longer. This is really quick, so just kind of depends, And so I'll probably ask something about that. And so most of these, you'll notice something interesting. Usually it's either a completely distributed load or triangular or a combination. And that's about all he's got. He's got some funny, weird ones here. So there's that's actually a combination one, because if you zoom in on it, you can make it, I don't know if my handwriting is, you can make it a triangular one on top of just a constant one. And so that's a combination. And so most all of them are that way. That's a combination of it too. Anyway. Yeah. Well, wait a minute. No, I don't have that ability here. There you go. That's a combination. I don't see anything that's not either flat or triangular that I've seen so far as I'm scrolling. That I don't even want to think about.
The one on I was measuring the final. It was a quadratic.
Yeah.
But I mean, you just take the integral of each part and have it together.
Right.
It's not like you have to take them all together. So it's simple enough to find. So long as you know the property.
Yeah. Did you get that one?
Yeah.
Okay. Yeah, and see, that's the thing. I threw that one out there. The only reason I put that one on there is to make people go back and look at doing the integral, and then that actually would make you think about, okay, I think I made it quadratic, so I had a constant term, a linear term, and a quadratic term. So if you think about the linear term, it's like a triangle. If you think about the constant term, it's just like a constant, So those two together are kind of what's in here. The only reason I added the quadratic is kind of put people in a position where, okay, I guess I'm gonna have to integrate this. And when they integrate it, at least they possibly saw where it came from and can go on from there.
Yeah.
And so it was kind of trying to be educational in a way, but it wasn't necessarily. And since I was given 5 tries on it, I thought, maybe you would learn a little bit by seeing a little bit of it. But in practice, that's probably not what you're going to see. You're going to see, more than likely, you're going to see a constant one or a linearly varied one. That's just nature. Even if you fill up swimming, like an aquarium, if you go fill up an aquarium, believe it or not, excuse me. So you got water in here. It turns out the load is exactly linear. If you look at a spillway, it's the same way. You build a spillway here with a big, huge brick, a bunch of piles of brick, and you got water back here. And what's happening is, the deeper you go, the more pressure there is. So this is a linear profile, and you really can't. I don't know, unless you do something really bizarre, like add an extra push or pull down there underwater, you can't get anything but a linear profile. So it's like, that's what it is. There's nothing more to it, So really, constant profiles are pretty easy, because if you're taking a bridge or laying a bunch of concrete on top of an I-beam, like out on the highway, usually, I haven't seen, I'm sure there might be somewhere, but I haven't seen anywhere where the depth of concrete they pour, maybe it's like 12 inches thick all the way across. So that means it's a uniform amount of weight, so it's an equal load on that beam. And so, you could do something crazy, like, but most people, they're not going to do that because it costs more money. Concrete is concrete. You order it from the concrete truck, comes out, it pours it. It generally is all about the same weight. The civil engineers who build the bridges, they specify it to be the same. So they want it to be the same. So, equally distributed or triangular distributed loads, that's it. So the quadratic was just thrown in there just because. So let's see, that was 7. So you said now 8 is a little bit of friction, and there was a problem or two on that, but the problems on friction were pretty easy that I put in there. Yeah. The friction becomes more of an issue. Okay, you'll go into mechanics and materials after this. And then after that, I think you go into machine components. I think there's a little bit in mechanics and materials on friction for belts and stuff, but there's more in the course after. So the course that we're looking at, if we just get the concept of, a box sits there and it's across, say this is carpet, and you already know when you're moving furniture, it takes a little bit to break it free. And if you oil the floor or you put something down there, it slips around real crazy, but you know that there's a friction. Well, it turns out, dry friction is just, if this is 100 pounds, and this might go up to 50, but they have this coefficient, say it's 0.5, then this is your normal force. You sum the forces in the Y, you get 100 pounds. And so the maximum that you can get here is 50, which is that number times that number. But you can put 25 pounds on it, but nothing happens. You can't move the furniture. You push it, push it, push it, and then finally it breaks free and you can start pushing it across the floor. So in a belt, it's similar, but the difference in a belt is, say, the belt could be wrapped around here, and I'm not doing a good job. So there'll be a tension in this pulley The belt may be spinning, and so it'll be touching all of this surface here, and it'll be wrapping around, and so what you're getting is, I'm doing a terrible job here. There'll be a normal force tying it on here, and there'll be a friction force that keeps it from slipping. And if it starts slipping, that's when you sometimes smell the thing burning, or you hear it squeaking, or something like that. That's a lot in machine component, and I think they cover that a lot, and a little bit in mechanics and materials. So for us, if we just learn the basic concept, that's pretty good, I think. There's more detail later on. So I guess they're all coming out of there, so they're probably gonna try to get us out. And that takes us to the centroid, and then the moment of area, and that's pretty much it. And I didn't say much about the moment of area, but that's used a lot in mechanics and materials. And the reason that is because, it turns out if you take a beam and you look at it and you say there's a moment there, and there is internally, it turns out that the way the moment shows up is through a distributed load that looks like that. And so at the very top, it's the maximum, or the very bottom, it's the maximum. And it turns out if there's a dude standing here looking at it, say it's an I-beam, you might see this. Oh, that's ugly looking. But it turns out there's more area here and a little less area here. So it turns out in the equation, you'll see, let's say XX. So you'll see this term for stress. And it turns out that's exactly what that is. You find out, I'm not doing a good job because the thing is, you'll find that out. And in mechanics and materials, they'll say, okay, I want to know IXX. Turns out MC over I, where C is the distance from that's going to be your stress that you see back in this funny drawing right here. And so you'll see this equation. It turns out that that's the term that goes underneath there. So in other words, think about it like this. If you take a beam that is a long, slender ruler, like that, you push on it, it's going to bow a lot. But if you take that ruler and turn it sideways, I'm not doing a good job here either with my drawing, it becomes stiffer. You push it this way, it's really stiff. And what you find out is I here is big compared to little. And it turns out that I has a lot to do with how stiff that beam becomes. Okay. And so that you'll learn in mechanics and materials. So it's not just we're learning this new term for the heck of it. This is the way it's been for years, but I wish there was a little way you could jump forward and back and jump forward and back, but So I guess we better go because I think they're going to want to get this. So that's all I'm going to do. If you have other questions,